In this video we're going to look at the derivation of the cubic spline. In other words, how do we create a cubic spline from zeta data points? We're going to assume that we have n data points, x values from x1 to xn and matching function values. If we have n data points, of course, we have n minus 1 intervals. And between each pair of points, point I and point I plus 1, we're going to fit a different cubic polynomial, fi. So a cubic polynomial has 4 parameters, ai, bi, ci, and di, and of course these will all be different for each one of the different cubic functions. And we're going to write our cubics in a particular form. We're going to say that fi of x is equal to ai plus bi times x minus xi plus ci times x minus xi squared plus di times x minus xi cubed. This is not really the standard way of writing a cubic, but it turns out if we write our cubic this way, we have certain advantages in that the mathematics for the cubic spline becomes a little bit simpler. So we have n minus 1 functions, f1 up to fn minus 1, and we need 4n minus 4 coefficients. However, how do we find 4n minus 4 unknown parameters from only n data points? Well, somehow we need to come up with 4n minus 4 equations. So let's have a look at how we can do that. First of all, we need that the function values at the interior points are equal to the data values. And remember, at any given point, point xi, we have two splines that match up there. First of all, the one on the left-hand side, which in this case is fi minus 1, and the spline on the right-hand side, fi. So the function value at the left-hand side has got to be equal to the function value from the right-hand side function, and both of them have got to be equal to the data value. That means fi of xi plus 1 has got to be equal to yi plus 1, and fi plus 1 at xi plus 1 has also got to be equal to yi plus 1. This has got to be true at n minus 2 points. Got to be true for 2 splines, so that gives us 2n minus 4 conditions. We also need that the function values at the end points are equal to the data values, and so what that means is that f1 of x1 has got to be equal to y1, and fn minus 1 at xn has got to be equal to yn. So this then gives us an additional 2 conditions. We also want the first derivatives from a left-hand spline to match the first derivative from the right-hand spline. So what that means is that the first derivative of the ith spline at xi plus 1 has got to be equal to the first derivative of the I plus 1th spline at I plus 1. And we want this to be true at the interior points. That again gives us an additional n minus 2 conditions. So we now have 3n minus 4 conditions, which are going to allow us to find these 4n minus 4 parameters. But we're still not done. We also need to match the second derivatives at the interior points, so that the second derivative on the left-hand spline at xi plus 1 has got to be equal to the second derivative of the right-hand spline at xi plus 1, so that gives us another n minus 2 conditions. We're almost at 4n minus 4. The only thing now we need 2 more conditions. Either the first derivative is specified at the endpoints, or the second derivative is specified at the endpoints. And you can actually mix and match. You can have a second derivative on one spline and a first derivative at the other end. Regardless, this gives us an additional 2 conditions and a total of 4n minus 4 conditions. So we now have 4n minus 4 conditions that will allow us to find the 4n minus 4 unknowns. What we're aiming to do here is to write our coefficients ai, bi, ci, and di in terms of our known values. In other words, in terms of the function values yi and also the values xi at which the function is defined. The derivative is not intuitive, okay? It requires quite a lot of algebra, and I'm going to go through it now. But I'm going to preempt the result so that we can maybe have a bit of an idea of where we're going and why we're doing what we're doing, and state the primary relationship we're trying to find to begin with is the relationship between the unknown coefficients ci and the function values that we've got, the yi. Once we've found the ci, we will then see how we can go and calculate the a's, the b's and the d's. Okay, so let's write the cubic spline just up the top here for reference. Let's let x equal xi and calculate what fi of xi is equal to. So if we plug x is equal to xi in the spline up here, we end up with this expression here, but we can see that all of these terms are xi minus xi. All of these terms are 0. So that gives us then that fi of xi is equal to ai. But we know that fi of xi is just equal to the function value, yi. This then gives us that the unknown coefficients ai are just equal to the function values that we've been given. So that's pretty easy, and indeed it's one of the reasons that we wrote our cubic like this expression here. Now let's define the spacing between adjacent nodes as hi is equal to xi plus 1 minus xi. So this is just the distance between our nodal points. It's just a shorthand notation that's going to make life a little bit easier for us. So the condition of continuity between adjacent splines we've already seen is fi plus 1 at xi plus 1 has got to be equal to fi of xi plus 1. So the left-hand side, directly from this expression up here, gives us that fi plus 1 of xi plus 1 is just equal to yi plus 1. Okay, so we've got the left-hand side of this expression. The right-hand side is just plug x is equal to xi plus 1 into the definition of the spline, and we get this expression here where these things can be replaced by hi, just using this definition here. Okay, so we've now got equation 1, which relates the function value at xi plus 1, in other words yi plus 1, to the function value at yi plus these coefficients here. We're going to use equation 1 later on in the derivation. Now let's have a look at the first derivative of the spline. So if we just take the first derivative of this expression here, we can see that that coefficient drops out, the x minus xi term disappears, the squared goes from here, we get a power of 2 out here, the 3 becomes a 2 here, and we end up with the first derivative of the ith spline is just equal to bi plus twice ci, x minus xi, plus 3 di times x minus xi squared. And of course, pretty much as we did before, if we evaluate the derivative of this spline at the point xi, these terms here drop out, and we can see that the first derivative of the ith spline at xi is just equal to the nodal coefficient bi. The condition that first derivatives are continuous at node xi plus 1 is simply written as that expression there. Therefore, the left-hand side of this, using this expression up here, just gives us that the first derivative of the I plus 1th spline at xi plus 1 is equal to bi plus 1. And substituting in to this expression at the top here, x is equal to xi plus 1, allows us to write that fi dashed at xi plus 1 is equal to bi plus twice ci hi plus 3 di h squared. So we can equate these two things, and we come up with an expression that relates bi plus 1 to bi plus twice ci hi plus 3 di hi squared. We're going to call that equation 2. We can do a similar thing for the second derivative of the spline. So if we take this expression up here, we take the first derivative of that, the bi term disappears, we end up with twice ci plus 6 di times x minus xi. And of course, if we substitute x is equal to xi into this expression, we just have that the second derivative of the ith spline at xi is equal to twice ci. Continuity of the second derivative at node xi plus 1 is written like this, and it gives us that twice ci plus 1 is equal to twice ci plus 6 di hi. We're going to call that equation 3, and we can actually solve equation 3 for the coefficient di, and gives us that di is equal to ci plus 1 minus ci divided by 3hi. So we have equations 1, 2 and 4 from previous slides. We need to now try and do something with these things here. So first of all, substitute equation 4 into equation 1. So substitute this expression here for di, and we end up with that expression there. And if we just group the terms, we come up with yi plus 1 is equal to yi plus bi hi plus this combination of c terms, which we're going to call equation 5. We can now solve equation 5 for bi. So bi is equal to some expression involving y's and some expression involving c's. Now remember, we're just trying to get a relationship between the y's and the c's. We're not quite there yet, but you can see where we're headed. Now if we just reduce the index in equation 6 by 1, in other words the yi plus 1 becomes yi and the yi becomes yi minus 1, we end up with equation 7. So equation 6 and equation 7 are effectively the same equation, just with a different index. So equations 2, 4, 6 and 7. Substitute equation 4 into equation 2. That gives us this expression involving bi plus 1 and bi. And if we just group the terms nicely here, we get equation 8. So bi plus 1 equals bi plus ci plus 1 times hi. Again, we can just reduce the index in equation 8 by 1. So we get a relationship now between bi and bi minus 1. We'll call that equation 9. If we substitute equation 6, equation 7 for bi and bi minus 1, and we substitute these things into equation 9, we get this expression here with y's and c's, and you can see we're now almost at the point we wanted to be at to begin with, where we have an expression that relates y's and c's together. So we'll just rewrite that at the top of the next page. The idea now is to move all the terms involving y to the right hand side and all terms involving c to the left hand side. If we do that, we get that expression there. If we now group the terms, so collect the terms involving ci minus 1, ci and ci plus 1, we end up with equation 10. hi minus 1 ci minus 1 plus twice hi plus hi minus 1 ci plus hi ci plus 1 is equal to a right hand side term involving the y's. So we have got exactly where we wanted to. We have a relationship between the unknown values c and our known function values y. However, it's not a straightforward system of equations. We can't solve it directly. So equation 10 can be written for the internal nodes. I goes from 2 to n minus 1. It's actually quite important here, and this is going to come back to be something that we're going to need to somehow deal with. When I is equal to 1, if we look at these two terms across here, we end up with an h0 and a c0. And this term here is a y0. So this equation doesn't exist for I is equal to 0. So that's problematic. We'll need to deal with that in a minute. That's why I'm saying they only go from 2 to n minus 1. So this has given us n minus 2 equations. As I've already said, there's n-1 unknowns, C1 up to Cn-1. Those are the things that we need to know. Okay, so this is our equation. I think we can see it's a tridiagonal system for our unknown Ci. So, leaving off equation for I is equal to 1 because there's a bit of a problem there. If we look at each of these equations, for 2, for 3, for n-2, all the way up to n-1, we can see that the equations can be written as a tridiagonal matrix. Now, we actually introduced an additional problem. We have a vector of unknowns here that goes from C1 down to Cn. So Cn actually appears in this equation here for I is equal to n-1. If I is equal to n-1, we'll end up with a Cn. The problem is, well, I've already said this is only n-2 equations. It involves unknowns C1 through to Cn. We've actually introduced an additional problem. Cn doesn't exist because we only have n-1 splines. So we're a little bit stuck at the moment because we have a system that's not actually a square matrix at the moment. It's got n-2 rows but n columns. We're going to need 2 additional conditions in order to sort this one out. One condition for C1 and one condition for Cn. Remembering that Cn doesn't really exist. Now there's a number of choices. They are natural spline, a clamped spline, a spline that's called not a knot, and a periodic spline. We are only going to consider natural and clamped splines here, and we'll do that in the next video.